University of California at Berkeley. He works on three manifolds topology and hyperbolic geometry. And let me mention some of his main contributions. In 2004, he proved the modern timeless conjecture, which essentially states that a hyperbolic three manifold with finitely generated fundamental group is homeomorphic to the interior of a compact three manifold with boundary. Around 2012, he proved the virtually Haken conjecture, which is attributed to Waldhausen, I think, and the virtual fibering conjecture, which is formulated by William Thurston. His research had many applications in three manifold topology, hyperbolic geometry, and geometric group theory. Professor Agol received a number of awards and prizes for his work, including the 2009 Clay Research Award for the proof of the modern timeless conjecture. In 2013, he received the Oswald Veblen Prize in Geometry, and he obtained the 2016 Breakthrough Prize in Mathematics for his spectacular contributions to topology and geometric group theory. So please welcome Professor Ian Agol. Thank you very much, Ian, for accepting to give this talk in this conference.
Yeah, thanks a lot for the introduction and the invitation. Hopefully next time I'll be able to visit Argentina. Unfortunately, you'll be hearing this talk coming from Berkeley instead. So today I wanted to talk about, so in your introduction, you mentioned some of the work that I've done in the past. And a lot of it is motivated by the ideas and questions of William Thurston, who was my mentor when I was a postdoc at UC Davis. In any case, he left a lot of interesting questions, and I guess I'm still continuing to work on them. So this is a little bit of a progress report on some of those other problems that I'll mention. So today I want to talk about the volumes of hyperbolic three manifolds. And let's see. So I'm not quite sure what the what the background of people are. So I'm planning on giving a fairly general sort of colloquium style talk, and because of that, I'm going to focus mostly on knots and links. So I want to talk about hyperbolic three manifolds, which is an important topic in three-dimensional topology due to the geometrization theorem. So I want to survey then a little bit about what's known about hyperbolic knot and link complements of small volume. So just focusing on the examples of links and knots for concreteness. So first I'll talk a little bit about three-dimensional topology and what it means and how we study knots and links, and then a little bit about hyperbolic geometry. And then finally, I'll plan to talk about some recent progress on volumes of hyperbolic link complements. So that's the plan for this talk. Okay, so first, what is three-dimensional topology? Well, we're interested in studying topology in 3 dimensions, and this is introduced originally by Poincaré to study differential equations and study the spaces of their solutions. And that was originally known as analysis situs, but has become known as topology. In any case, we're interested in studying spaces up to deformation. So the classic example is that a topologist, in particular a three-manifold topologist, can't distinguish a donut from a coffee cup because you could, by continuous transformation, transform the donut into the coffee cup. And so by transforming, I mean you can do sort of smooth or continuous deformations which don't glue or cut. So that's the usual notion of of equivalence here. Really, in 3 dimensions, we're talking about isotopy, so a continuous deformation that sort of extends to all of space. So if you cut, then you're doing something where the subspace is getting changed drastically. But what about this donut and this coffee cup? Are they the same? Well, so this donut here is a usual donut. This coffee cup now, coffee mug, has a a little tangle in it. Well, is it a non-trivial tangle? Can you undo it without cutting or without gluing? So these two objects here are homeomorphic. So there's a one-to-one continuous bijective with inverse correspondence between them that preserves the topology. But the question is, can we deform one into the other? Well, you might guess that this is a non-trivial donut on the right here. It's not necessarily equivalent. Oh, so there's a I have a question here. Let me just yeah. So feel free to chime in with any questions as we go along. So these two objects are intrinsically homeomorphic, but actually they can't be deformed. This donut on the left here can't be deformed into this coffee cup on the right. So how does a 3-manifold topologist, a knot theorist, tell this? So what these objects are, so really what we need is a donut that sits in space a little differently. This is called, or what 3-manifold topologists refer to as knots. So you can think of this as a thickened up closed loop of string. And this coffee cup, if you were to deform it down, if it was made out of clay, then you could deform it into also a closed loop, because this the cup that we see there can be deformed continuously down and flattened out without any sort of cutting or gluing. So this is topologically, this is a knot. And so we call these knots, referring to closed loop of string. It's a sort of mathematical model for that. So how do we tell if two of these knots are equivalent by deformation, what we call isotopy? Well, the usual thing that 3-manifold topologists do is we don't look at the knot, but we look at its complement. So here's an example of a complement. So if we start with another picture of our donut, well, we can think of this as sitting not just inside of R3, but inside of S3. There's a point off at infinity, the 3-dimensional sphere. So it's the Alexandrov 1-point compactification, if you like. So we can take this donut and we can poke a little hole in it. And if imagine it stretch out a rubber, you may have even done this before with an inner tube. You can stretch it out and keep on stretching it until the hole becomes engulfs the entire tube that we started out with, and then shrinks down again, and we've turned the inner tube inside out. Now, what's happened to this little disc here that we've cut out and and then replaced again at the end? Well, what it does is it sort of travels around and it goes through the point in infinity in S3 and then closes back up again. So what we've done is a continuous deformation, not inside of R3 of the entire surface of the donut, but inside of S3. So we've taken the inside of this donut here, and we've converted it to the outside. So if I were to draw like a little loop inside of here, in the endpoint, this loop would now lie on the outside. So that's what we mean by taking the complement of a knot. Well, what if I take a more complicated knot, like this blue figure 8 knot here, and so I take its complement. So I'm Xing out the blue. So I remove this from the 3-dimensional sphere. Well, if I do this process of flipping it inside out, like we did with the inner tube on the previous page, then we get the figure 8 knot complement. We get something that looks like a ball with this knotted hole going through it that is a copy of the figure 8. So it's like a worm that ate a knotted hole through an apple. And so this is what we want to look at. Now, if we look at the complement of this solid torus here, it's homeomorphic to a solid torus, but its complement has non-trivial topology. So if we have two knots which have distinct complements, well, if they were isotopic, that isotopy would the complement would get dragged along, and you would get homeomorphic complements. So if we can show two knots have distinct complements up to homeomorphism, then we've shown that they're not isotopic. So under the isotopy of a knot, then the knot complement is an invariant of that isotopy, and so the homeomorphism type of the knot complement turns out to be a non-trivial invariant. So two knots with different complements then up to homomorphism could not be isotopic. And so what knot theorists want to understand are invariants of these knot complements. So the classic example is to consider the fundamental group. But today I want to talk about another invariant, which is the volume of a hyperbolic knot complement. So we'll look at a certain class of knots and links, which are hyperbolic. Okay, so, well, how powerful an invariant is this homeomorphism type of a knot complement? Well, Gordon and Lukey proved in 1989 that two knots with homeomorphic complements are actually equivalent up to isotopy or taking mirror images. So you might have a homeomorphism that reverses, if I reflect through a mirror, that's a homeomorphism, and that reverses the chirality of the knot. But up to that operation, so actually the oriented homeomorphism type of the knot complement is a complete invariant of the isotopy class of the knot. So it's a bit hard to visualize. I mean, this took me a while, even as a graduate student, to understand what this theorem meant. But a priori, it could be possible that you could have had two knots, which you remove them from the free sphere, and their complements become homeomorphic. So the point is that the homeomorphism between their complements would not extend to 3 space. So they would be sort of you'd fill in the donut in different ways, what's called Dane filling, which I didn't want to get into. But anyways, this phenomenon does exist in other 3 manifolds other than the 3 sphere. And in fact, as we'll see also, that there's examples of links that have homeomorphic complements even though they're not isotopic. So there's a little extra data that you need in general to not just a homomorphism of knot complements, but some data about how the homomorphism behaves on the boundary tori that is enough to recover the link complement. And so in fact, it was proved by Waldhausen in the 70s that and Hemian that this gave actually this method of understanding the homeomorphism type of the knot and link complements gave a complete answer to the isotopy problem for knots and links. So now I want to move on to hyperbolic geometry. Was there any questions on or clarifications on 3-dimensional topology or knot theory? This is a admittedly very brief sort of introduction or overview. Okay, so so now let's go to talk about hyperbolic geometry. So non-Euclidean geometry or hyperbolic geometry was discovered by Bolyai and Lobachevsky, and also I guess independently Gauss, as an example of a non-Euclidean geometry where the parallel postulate fails. So if you, the simplest example maybe is the Klein model, where you take a disk in the plane and you see that for a line here, there's many lines which are not parallel to it. So it fails the parallel postulate, and yet you can put a metric on there, or a notion of distance and angle, which makes it satisfy the other postulates of planar geometry. And so, so this was an example of that was showing why the parallel postulate was necessary in Euclidean geometry. Here's a picture that's been crocheted, and you can see here. So if you crochet in a way where you make stitches in each row, you add an extra number of stitches, then you get a saddle-shaped surface that behaves sort of like the hyperbolic plane geometrically. And here there's an example of a line, and lines that are not, that go through a single point, which are parallel to this one. They don't meet it. Here's a picture of the Poincare model, where now geodesics are circles orthogonal to the boundary. And this model has the advantage that the angles are correct. So if you measure the angles between two two lines in the Euclidean, in our Euclidean perspective, then you get the same angle as in the hyperbolic perspective. But the circle here is sort of infinitely far away. And then another model, which will generalize to 3 dimensions, the upper half space model, where geodesics are circles orthogonal to the boundary, as in the disk model, or they can be vertical lines as well. So let's look at the 3-dimensional analog of this. So consider a chunk of glass sitting on a tabletop, and this glass has very special properties, that the speed of light in the glass, as you go towards the table, the speed of light is proportional to the distance to the table. So as you get closer and closer to the table, a light ray would slow down. And because the speed of light is proportional to the height above the table, it can never actually reach the tabletop, because it goes slower and slower as you go down. And so, for example, then you can measure the distance between 2 points by how long it takes light rays to go from one to the other. And this is, I'm assuming that this is a homogeneous medium, that the speed of light is the same in all directions. In theory, one could try to make a chunk of glass like this via vapor deposition or something. I've tried to ask physicists to do this before, but as far as I know, no one's actually made some model like this. But in any case, if you had this chunk of glass with this varying index of refraction or speed of light, then it could in principle give a physical model of hyperbolic space where length is measured in the time that it takes light to get from one point to the other. And then when if you were to make a chunk of this and you put mirrors on the side of some nice figure, you could look inside of it and see this kind of 3-dimensional kaleidoscope of hyperbolic space. And I'll show some figures later, or we saw one on the title page, of what it might look like inside of hyperbolic space if you were able to manufacture something like this. So light, because it's slower near the boundary, if I want to get from one point to another that are around the same height, it's faster to go up, where you can move, where light can move faster and then come back down. And so if you work it out, then the light rays will move along these geodesics that are perpendicular to the boundary, as we saw in the half space model in the plane. And again, this is a conformal model, so distance is measured via these light rays. Angles will be the same as the angles as in the Euclidean metric. And then light rays will be either vertical geodesics, which are kind of limiting of larger and larger geodesics perpendicular to the boundary. So, so really what we're interested in then is this model. It's really a Riemannian metric, a constant sectional curvature -1. And if you look at complete simply connected manifolds with constant sectional curvature -1, they will be isometric to this upper half space model. That's technically what we mean here. So so let's talk about then a hyperbolic manifold. So a hyperbolic manifold is locally modeled on that metric. It has a distance metric, which if you take any little ball, it'll look like a little chunk of this manifold. So I'll just give the definition then, at least for orientation preserving, orientable hyperbolic manifolds. Well, the orientation preserving isometry group of hyperbolic 3 space is PSL2C. So the action of, so if we look at our upper half space model, this table here is really a copy of the complex numbers. And if you compactify it, then you get C hat. So we put a point, there's a point sort of at infinity. And if we add that point, then we get C hat or CP1. And if we look at the action of PSL2C acting on CP1 by Mobius transformations, you know, A, B, C, D, times the UV, so just acting linearly will be, so the action will be, sorry, if we take like Z1 or something, the action will be AZ plus B over CZ plus D. In any case, this action on the complex plane extends to all hyperbolic space in a natural fashion, in a conformally unique way. And so this can be, there's explicit formulas via, say, the quaternions that I didn't want to write down, but in any case, one can show that's the orientation preserving hyperbolic isometry group. You get to all of the isometries by adjoining the mirror reflection as well. So now take a discrete subgroup gamma in PSL2C. So by discrete, what I mean is that the identity element is isolated. So there's no sequence of points. It's a little hard to draw, but there's no sequence of points converging to identity. And if the identity element is isolated, then every other point will be isolated. And then when you take H3 modulo this group, you get well, in general you get an orbifold, but if we also don't allow any elements of finite order of the identity, then we actually get the quotient space cosets of this group form a manifold. It's actually, you can think of it as double coset. So you take PSL2C, you modulo on the right by gamma, and on the left by the isotropy group of a point, which is a copy of SO3. So this metric on H3 is isotropic. You can rotate uniformly around a point. And again, this is equivalent to saying that we have a three-dimensional complete Riemannian manifold of constant sectional curvature -1 via some classic theorems of Riemannian geometry. And if you have a hyperbolic manifold, this gamma that you have that gives this manifold with this metric is unique up to conjugacy in PSL2C. So it's not quite unique. Okay, so so we'll see some examples in a second. I'm sorry I didn't give any examples yet, but now let's go back to our NotComplements. So a discovery of Thurston in the 70s was that most, in some sense, NotComplements emit a geometry modeled on hyperbolic geometry. So they, if you give this knot, then there's some group gamma, and so you have a faithful representation, discrete representation of the fundamental group of the NotComplement into PSL2C. And this was actually presaged by work of Rob Riley, who discovered an example of the figure 8 knot. So what Thurston showed, and this is, you using some previous work of Jacob, Shale, and Jorgensen and others, there's this trichotomy that you have knots which are torus knots, so you can draw them on the surface of a torus. So you can draw them on a donut, in other words, an unknotted donut. Or they're satellite knots. So you take some what's called a pattern knot, and you tie some more complicated knot inside of it. So and I guess the torus knot can be thought of as a satellite of the unknot, but it's special from the way that it behaves. And so if you have a knot it's not a torus knot and it's not a satellite knot, then what Thurston showed is that it's a hyperbolic knot, such as the figure 8 knot. And again, there is examples, as I mentioned, due to Rob Riley, that that then he generalized to all knots. Connect sum is also a satellite knot. You can think of this knot here as a satellite. It's sort of orbiting around this trefoil knot, or vice versa. So if I shrunk this down, then it would look like I took the trefoil knot and I tied a little knot inside of it. So in this case, either one of these knots could be the pattern knot in which you're tying a satellite of. So so these satellite knots, in some sense, they're this sort of canonical sort of connect sum or decomposition into simpler knots, or there's a sort of calculus for how you decompose these. And so the fundamental things to understand in 3 dimensions are somehow hyperbolic knots and torus knots. Well, torus knots are essentially described by rational numbers. It's a slope on the torus. It'll be determined by some rational number that's telling you how many times it winds around one way and how many times it winds around the other way. And so they're much easier to understand in some sense. And so the hyperbolic knots are less well understood. So now we get an invariant of a hyperbolic knot. Well, one invariant is, for example, the conjugacy class of the fundamental group in PSL2C. And a remarkable thing then is that's in some sense a complete invariant of the knot complement. So this gives a new solution to the isotopy problem for knots that was solved originally by Waldhausen, but Thurston's theorem in some sense gave a new way of achieving the homeomorphism problem. So let's look at hyperbolic volume. So here's a picture of the figure 8 knot complement again. And it turns out that, so, Rob Riley, Bill Thurston showed this is a hyperbolic knot. Here's a fairly explicit way to see what the hyperbolic structure is. So what you do is you take these, what are called ideal tetrahedra. So these are polyhedra in hyperbolic space. If you drew them in the Klein model or in the Poincare model, they would just be in the Klein model, it's just a finite tetrahedron. I hope to show an example of this at the end with a computer program, Snappi. But in any case, if you take these ideal tetrahedra and you glue them in the fashion shown here, so you take this polyhedron here, the vertices here are at 0, -1, and omega, which is e to the 2 pi over 3, and then this is omega plus 1, which is e to the I guess pi over 3. And then you draw these vertical geodesics connecting up these 4 points. There's a point at infinity here that these rays are going to. And now I glue B to B prime, C to C prime. There's an isometry taking that to that, and A to A prime. So I glue these tetrahedra in this fashion. This can be done just as gluing a pair of simplices, and then removing the vertices. So the vertices of these simplices are off at infinity, and they so you get this kind of cell complex realizing the interior of this manifold, but with that's infinite diameter, because as you go to infinity, the distance goes to infinity. And where does the knot lie here? Well, the knot is actually coming from, there's sitting above this region here, there's this infinite rectangle crossed with a ray. And this region has finite volume. You're integrating 1 over n cubed over this region. And in fact, the volume will be 1/2 the area of this rectangle if we put this rectangle at height 1. So the knot is actually, when we do these identifications, the boundary of the knot is this red torus here, and that will be sitting in the quotient here. So the knot is, but you can push it off to infinity. So in some sense, the knot is pulled like taffy off to infinity, infinitely far away, if you think about the metric. Now because these infinite parts, and so these other parts here will get, so I think I haven't described this completely right. These other guys will actually get glued up to form this torus. You chop off the corners of these tetrahedra, which are infinitely far away, to get the torus. In any case, you get this, each of these simplices has finite volume. When you glue them together, you get something of finite volume, and it's actually complete metric, which needs to be shown. But the volume of this is just the sum of the volumes of these tetrahedra, which has an explicit formula, something like 2.0298. And it has an explicit formula in terms of an infinite series. Okay, so that's the invariant that I wanted to investigate today. Is there any questions or comments? Okay, well, let's continue then. So now let's talk about hyperbolic link complement. So link is a collection of knotted donuts, knotted string, and Thurston's theorem applies to links as well. You have to be a little more careful what you mean by a satellite or whatnot. But in any case, these are two examples of links whose complements admit a complete hyperbolic metric of finite volume. So now the theorem of Mostow implies that if a hyperbolic link, or if a link has hyperbolic complement, then that metric is unique up to isometry. And so in particular, again, this gamma that we have, this discrete representation of the fundamental group into PSL2C is unique up to conjugacy. And again, it can give you an effective way of solving the homeomorphism problem. Now, the caveat here is that for links, you can have different links that have homeomorphic complements that are not isotopic. So again, you have to keep track of a little more information. If you keep track of, say, the meridian of each of the loops together with the homeomorphism type of the complement, then you do get a complete invariant of the link complement. So here, what you can do is I have this disk bounding, say, this unknotted component, and I can cut along there and put some twists in and then glue again. I'll show more examples in a second, but to get links with homeomorphic complements. So we're essentially adding some twists between these two strands of the yellow component here, and you can do a similar thing with the bromium rings, where you can add twists in and get links that have homeomorphic complements. But if you keep track of this extra data, this peripheral element, together with the homeomorphism type of the complement, then it does become a complete invariant of the isotopic class of the link. And again, there's effective algorithms for computing these things and for solving the isotopy problem. So now I want to talk about a special class, actually, that we've already encountered some examples of, which are called cusp arithmetic manifolds. So we have one slide on this. This is a special class of arithmetic manifolds. So we take a quadratic imaginary number field. So D is a positive square free integer, and then we take the field which is Q adjoin square root of minus D, and now we can take a subgroup of PSL2C, which is PSL2OD. So these are 2x2 matrices with entries in OD. So AD minus BC equals 1. That's what the S stands for. It's the special linear group, and A, B, C, and D are in the ring OD. And essentially because OD, so what's special about a quadratic imaginary number field is that its ring of integers is a discrete subset of C. So for an example, you take Z adjoin I is just Z plus ZI. So as a subset of C, it's just a discrete square lattice. So you have 0, 1, and I. And so because that's, so all the entries of these matrices are discrete in each factor, and so it becomes discrete inside of PSL2C, or inside of this hyperboloid inside of PSL2 of 2x2 matrices. So this is an example of a discrete subgroup. In general, this will have torsion, but you can take a finite index subgroup which doesn't have torsion and get examples. So these examples are called Bianchi groups, and these were classically studied in the 19th century. And these account in some sense for all non-compact arithmetic hyperbolic three manifolds. Now I haven't defined arithmetic. It's a little bit involved definition involving algebraic groups that was investigated by Borel and Harishchandra. But in the case of hyperbolic three manifolds, which are non-compact, this essentially accounts for all arithmetic examples up to bounded index. So up to taking finite index subgroups and finite index supergroups. So if you take any arithmetic cusp hyperbolic three manifold, there'll be a finite index subgroup that's a finite index subgroup of one of these Bianchi groups up to conjugacy. So now let's take gamma to be a subgroup of a Bianchi group of finite index, which is torsion free. Then this will be a manifold of finite volume. More generally, you get for Bianchi groups, you get orbifolds. And then we take the discriminant of the number field. So it's either D if D is congruent to 3, or it's 4 times D otherwise. Remember, D is a square free integer. And then the ring of integers has an explicit formula in terms of the discriminant. So well, if we have 4D here, then this will just be essentially square root of D. But if D is congruent to 3, then if D equals 3, then you would get oh, and I have a sign error here. This should be a minus D here. I had it's a quadratic, so you take the square root of a negative number. So you have like 1 plus square root of minus 3 over 2 is an algebraic integer in O sub 3. Then there's a formula of Humbert that states that the volume of this quotient space is has an explicit formula in terms of a zeta function. So you take the zeta function of the the number field Q adjoin square root of minus D, evaluated at 2, and then times some factors that depend on the discriminant. And so this has another formula here. So you take the d to the 3 halves or 24, and then this function here is the Kronecker symbol. It's a periodic. It'll be periodic modulo d, but it's related to the quadratic residue. So if n is prime, then this is the Legendre symbol. It tells you it's 1 if minus d is a quadratic residue modulo p, and it's -1 otherwise. And then you extend this multiplicatively to all integers to get the Kronecker symbol. Anyway, just to give you a flavor of where these formulas come from, number theory. So there's nice examples of hyperbolic manifolds with explicit formulas for the volume. Any questions on arithmetic groups? Yeah.
Yeah. If gamma is not of finite index, then the problem is that it doesn't have finite volume.
Yeah, that's right.
Yeah,
so
okay.
then, then the volume's infinite, and that's another.
It's infinite. Yeah.
Yeah. So there's a large literature. So these are called Kleinian groups, and studying the infinite covolume ones is a big topic as well that I'm not touching on today. But yeah, that's and we know almost nothing about the case when these are infinitely generated. So that's still an active area of study. Yeah. Thanks. So for a general hyperbolic free manifold, not these arithmetic ones, the volume can be computed using the dilogarithm function of algebraic numbers. So there's some formulas, and these are what Kontsevich calls examples of periods. They're numbers obtained by integrating an algebraic function over a real algebraic variety. And there's programs to compute these hyperbolic structures. One of the first examples that was general purpose was written by Jeff Weeks with the help of numerous people. He's worked at the Geometry Center in Minnesota for a while, and that's called the program's called Snappi. That was available on Mac OS. Unfortunately, it's no longer supported. You need an old Mac computer to be able to run this. I actually keep one on my desk just to run Snappi, but there's newer generations of this Snap and Snappi, which is based on the Python programming language. So Oliver Goodman wrote Snap, which did a rigorous computation. So Snappi is it's not a rigorous program. If it succeeds in finding a hyperbolic structure, then it's giving you some indication that it's there, but it's not a proof. Snap is useful for actually giving proofs of rigorous verifications of hyperbolic structures. Snappi, written by or is maintained by Kohler and Mark Kohler, Nathan Dunfield, and others, uses the Snappi kernel, but with this Python interaction. So hopefully, if I have time at the end, I'll try to demonstrate that program a little bit. So these have been extremely useful for studying free manifold topology, and they give practical solutions to the homeomorphism problem. So if you find some knot and you want to figure out which knot it is in the knot tables, you can draw a picture on it with Snappi, and I'll hopefully, yeah, if there's time, I'll demonstrate that later, and then you can tell which knot in the tables it is if it's one of the known ones. If it's too big, then it might fail, or if it's not hyperbolic, then it also might fail. But there are techniques for dealing with that via a program called Regina by Ben Burton. In any case, what would it look like to be inside of a space with the hyperbolic geometry? So here's some renditions of what it would look like in the Bromian rings complement. Here's a picture of a fundamental domain for the Bromian rings complement in the Poincare model of hyperbolic free space. So I've taken the upper half space model and stereographically projected it to the ball, and so what this region is, it's showing how a fundamental domain for the fundamental group action. So if you take this and you take all the translates by gamma, you're going to get tiling of hyperbolic space, except for where things get identified. So these blue faces get identified, and there'll be other colored faces that get identified in pairs. Okay, so this hyperbolic metric on the bromine rings complement has finite volume. This is from this NotComplement video, which I recommend viewing if you haven't. That also was made at the Geometry Center, and the volume is 7.3 something. It's 8 times Catalan's constant. Again, it's another special. This is an arithmetic link, so this is a multiple of a special value of a zeta function, but it has this alternating sum formula. And so the remarkable thing is that Catalan's constant is not known to be irrational. It's actually, I think, believed to be. And in fact, Frank Caligari has shown that if you look at this series over the 2 adducts, then you actually get an irrational number. So there's some evidence that this might be irrational. But we would like to know more than that. I'll mention again later what we'd like to know. So we can talk about the volumes of link complements, and Thurston and Jorgensen then showed that for any given volume, there are only finitely many link complements with that volume. So for example, here, the Whitehead link, up to homomorphism. So again, there's this issue of twisting, but if you look at the homomorphism, here, I mean, many link complements up to homomorphism, not up to isotopy. And here's the -238 pretzel link. This has 2 components, maybe a little hard to see, but these 2 link complements have hyperbolic metric with the same volume, which again by Master rigidity is a topological invariant. It's given by this 4 times Catalan's constant, so it's half the volume of the bromine rings, and they're actually commensurable with each other. They have finite subgroups that are isomorphic. So but again, you can, even if, so volume is a very powerful invariant. It's finite to 1 on hyperbolic manifolds. And even ones that have the same volume, there's, again, the program Snappi or Snappi has other invariants of that structure that will allow you to distinguish them in principle. So here's a picture of some pattern that's invariant under the fundamental group. Each of these balls here sort of corresponds to a peripheral subgroup, so 1 or 2 conjugacy class of 1 or 2 of the peripheral subgroups of these of the fundamental groups of these link complements. And here's a picture for the -238 pretzel, and you see how they look quite different. And so you can distinguish these things via more refined information than volume. So now these volumes, Jorgensen and Thurston showed also that these are the volumes are well ordered. So if you take any decreasing sequence of hyperbolic volumes, that will be finite. So you can have limits for increasing sequences of volumes, but any decreasing sequence of distinct hyperbolic volumes is finite. So limits can only increase. So this is sometimes then referred to the volume spectrum because it sort of looks like a light spectrum, and the order type is omega to the omega. So and I'll explain a little bit more about that in a second. So as an example, this is from Thurston's notes. So here's the figure 8 knot, and if we add twists in that, so if you think of taking the Whitehead link and doing twists around one component and then erasing it, then you get this sequence of twist knots. And we see that, so the next one has volume 3.16, 3.42, et cetera, and then it converges. So as you put more and more twists in these things, you get, it's converging to the volume of the Whitehead link complement. And there's a certain sense in which these metrics, the hyperbolic metrics here, are converging. In the Gromov-Hausdorff topology, they're converging to the metric on the Whitehead link complement. And these twists here, there's a very short geodesics going around these that are sort of becoming this cusp in the limit. Again, I didn't really want to get into the details of how this works, but just to give you a flavor. So so the volumes here can have an increasing limit. That's this 2-component link. So Thurston has an influential paper in the 1982 bulletin, the 3-dimensional manifolds, Kleinian groups, and hyperbolic geometry, that sort of described his theory. And he asked 24 questions there, which have been quite important. So 2 of those questions, many of them have been satisfactory answer, but a couple of them are sort of open-ended. So 21 was develop a computer program to calculate hyperbolic structures in 3 manifolds, and that's what Jeff Weeks and these other people have done. And 22 was tabulate the volumes, well, Chern-Simons invariant I'm not getting into today, but other simple information for a bunch of 3 manifolds like knots and in the knot tables, and try to develop a practical feel for the well ordering. So Jeff, in particular, we'd like to know what is the minimal limit volume, or what are the minimum n-fold limit volumes, for example. So Jeff Weeks' program, as I said, in some senses answered 21, or again, it's kind of an open-ended question, so it's will probably always be open in some sense. But question 22 is then in principle asking, what are these manifolds that that achieve the different volumes in the volume spectrum. So people have taken 8 tetrahedra and glued them together in all possible ways and plugged them into Snappi and see what manifolds they get out. So in particular, Champion-Urquhart, Kaufman, and Mullen in 2014, they looked at all 8 tetrahedra ideal triangulation. So you take simplicial complexes with 8 tetrahedra, where you remove the vertices and you get a hyperbolic manifold. So you glue the tetrahedron in pairs, and here's the simplest examples. It looks somewhat different from the knot tables, which are ordered by crossings, but these are ordered by volume here. And again, this is just 8 tetrahedra, so it's not a proof that these are the simplest ones, but you see these twist knots showing up here. And this one, I think, is the -237 pretzel knot, which happens to have the same volume as the 5 crossing twist knot. In any case, so here's sort of a partial answer to Thurston's question 22. But what I'm interested in is, to some extent, is how do we rigorously find these things? So so what people have done is found the smallest links of volumes for 1, 2, and 4 component links. So Sal and Meyerhoff in 2001 showed that the figure 8 knot is the smallest volume hyperbolic knot with volume 2.029. And then in 2009, Gabay, Meyerhoff, and Milley showed that this 5 crossing knot, and also the -237 pretzel that this guy here, which has the same volume, are the smallest volume, the next smallest volume knots. In 2010, I showed that the Whitehead link complement, and again, there's infinitely many homeomorphic complements, but up to homomorphism of the complement, and the -238 pretzel, which have the same volume, these are the smallest volume 2-cusp hyperbolic manifold with volume 3.66 something, 4 times Catalan's constant. And then Yoshida in 2012 showed that there's a family of 4 component links, including these here, that have volume twice that, the same as the volume of the Bromian rings. But remember, the Bromian rings has only 3 components. It has the same volume, but it's smaller as this 4 component link. So, but it's smaller number of cusps or number of components. Okay, so that's what we know. So what about? So I skipped over 3 here. So one of the nagging open questions is, what's the smallest volume for 3 cusps? So, oh yeah, so there's a question about the Cantor-Bendixson rank of the set of volumes. I'll get to that in a second. Yeah, thanks, good question. So the proof that of these first 2 theorems here are computer-aided. So they did a computer search through a certain parameter space, and after that search and some theory behind it, they were able to show that these are the smallest volume using kind of packing arguments and various estimates. So the proof of this theorem is using a theorem of myself with Storm and Thurston from 2007, which uses minimal surfaces and actually the Ricci flow of Perelman. So we show there's a certain surface in the knot complement. You can cut along it, double, and then run Ricci flow, and you show that the volume is greater than some some volumes of some manifold with totally geodesic boundary. And so this was an application of Perelman's work that went beyond the proof of the geometrization theorem. But the open question is that I'm interested in is what is the smallest volume hyperbolic link with 3 components? Why is 3 harder somehow? And conjecturally, it's the 3-chain link with volume 5.33 something, which is less than the volume of the bromium rings. And again, this is an arithmetic link, so it has some formula. This is associated to find index subgroup of PSL207, and so it has this explicit volume. And here's a picture here that came from Snappi. So the conjecture then, my student Yu Zhang last year made some progress on this conjecture. It's a little technical to state, but he showed that either the volume of the 3-cust hyperbolic link is at least 6G 5.49, which is greater than 5.33, or there exists a certain submanifold, which is called a sutured manifold with Euler characteristic -1. And we conjecture that the smallest volume of this is this 5.33, the volume of the 3-chain link. And we have some progress on this conjecture. We've ruled out lots of different cases, but we haven't completed that. So these certain submanifolds that are hyperbolic metrics with geodesic boundary, we expect that this is progress on this question because these sort of manifolds ought to be easier to analyze. There's various techniques you have in the bounded case that you don't have in the cusp case. So the conjecture that we have is this is the smallest volume, sutured manifold with totally geodesic boundary. There's a hyperbolic metric here now where these trace punctured disks are totally geodesic, and then it's drilled out instead of a link. It's drilled out. There's a tangle we drill out. If you glue the top to the bottom, you get this 3-chain link. And so we have some ideas or evidence as to why this should be minimal. If we can rule out the case when the top and bottom are punctured tori, then that would imply this this conjecture. So now there's a question about the Cannabinic Index. So it's the rank is omega to the omega. So to summarize this table, we know the smallest volume one is 2.0298, and then we have 2.828, and then the next one might be 3.164. It's one of these twist knots that appeared in Thurston's table. Now, so the first limit point as you go around this, so that is 3.66. That's what I proved, this whitehead link. And then you look at limit points of double limit points. So this corresponds to one, 1, 2, 3. If you look at the ordinal type, and this would correspond to omega, and this would correspond to omega squared, but we don't know that. And then Yoshida's result would corresponds to, so we know what omega fourth is. And then the conjecture is that the theorem of Jorgensen and Thurston is the order type is omega to the omega. So we have, so n cusp links, omega to the n will correspond to the smallest, well, there's a shift here, so it's the smallest n+1 cusp link complement. Actually, we don't know the smallest, we just look at manifolds, we don't know the smallest volume ones will be links. They just happen to be, when you find the smallest volume manifolds, they happen to be link complements, which is why I focused on links today. So anyways, the open questions, what is omega to the n in general? Some other open questions are these volumes of these Bianchi groups, are they linearly independent over Q? So this is an issue of how do you tell if two manifolds have the same volume? And there's some deep conjectures in number theory that would imply that there's a method. Okay, so that's it for today. I guess I'm out of time, so I'll stop there. Thanks.
Okay, thank you very much, Ian. We have the question of Mariano Suarez Alvarez. Is the Cantor-Bendixson rank of the set of volumes known?
Yeah, so I think if I understand that right, I think this describes the Cantor-Bendixson rank. So this, let's see, the Cantor-Bendixson rank, I think, is how you take all limit points and you remove them, and you take all limit points and you remove them, and you repeat that process. Mm-hmm. And so I think what happens here, so if if you remove this, the first, or sorry, you remove the isolated points. I got it backwards. So you remove the isolated points here, and you're left with just the limit points, and then you remove the isolated points there. So, and you repeat that process. Then, so the Cannabinic Index should be omega, if I understand that right. But I'm not an expert on that sort of thing. But does that answer your question? I think it.
Are there any questions? I have one question. You show us a table of the smallest volume links with 1, 2, and 4 yes, one components. Yes,
components. Yeah.
But components. Yeah. But so is it possible to find a link of, I don't know, 5, 6, 7 components with smallest volume than a knot, than the smallest volume knot, or not? I mean,
good question. Yeah. So we do know. Well, okay, yeah. If you're focusing on knots and links, then that's not clear. If you allow hyperbolic manifolds, we know that the smallest n-cusp manifold will have volume greater than the smallest n-1 cusp manifold. They're related by what's called Dane filling, but that Dane filling might take you out of the category of knots or links. So anyways, I was just focusing for concreteness on knots and links today. But yeah, that's a good question. In principle, I guess you could have an n component link with volume less than the smallest volume in an n-1 component link. We don't, let's see, I don't think we even know that actually. So we do have lower bounds on the smallest volume n-cusp link, but I think they're not strong enough to show something like that because they're only up to some factor. Yeah, that's a good question. But yeah, in manifolds, then it would be true, I guess.
Here, I don't know if you can see the question of Mariano Suarez Alvarez. Can the volume spectrum be realized meaningfully as the actual spectrum of a linear map?
Oh, yeah, good question. Yeah, no, I think it's more just a poetic analogy. Yeah, not that I know of. I mean, unless there's some general theorem saying any well-ordered set has some realization. I don't know. Yeah, I think it's more just the fact that it sort of looks like you have these, the fact that it's order type omega to the omega. I think there's some spectra of molecules or something that has a similar structure, and that. But yeah, it's just there's no meaning other than just usurping the terminology from a different field.
Okay.
As far as I know.
Okay, so are there any other questions or remarks? Okay, so we thank again Ian for this beautiful talk, and again thank you very much for giving this talk at this conference. Thank you very much to the audience for coming here, and we hope to see you here in Buenos Aires after this pandemic.
Yeah, that'd be great. I would love to visit. Yeah.
Good. Okay. Thank you very much, everyone.
Andrew Nickus had a question, or was there? Oh, maybe not.
No.
Okay.
Somebody raised hands. Wait a second. There is a raised hand. Let me see who.
I can't see nothing.
But now he lowered it. So okay. So let's finish here. Thank you very much.
Okay. Thanks a lot.
Thank you very much.
Thank you. Bye-bye.
All right. See ya.